Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. Today we will start with part 3 for chapter number 2 for the cascade blade. So for this part, we will start with cascade blade analysis. So when I mention about the analysis, that means that we will learn about few equations. So in this subtopic, we discuss especially the equation for forces for cascade blade. So this equation will use as a basic equation to determine other type of equation that we'll use in cascade blade. Okay, the analysis of the cascade blade forces. So now we will discuss or we derive the equation, the basic equation that we will use for cascade blade analysis. So in terms of cascade forces. So before we continue about the derivation of the equation, so we need to make some assumption in order to simplify the analysis, to simplify the derivation of the equation. Our first assumption is the fluid flow is an incompressible flow, where we will use Mach number, low Mach number, which is equal to 0.3, and the compressibility effect is neglected. The second assumption is the fluid flow or the devices that we consider in the analysis, we consider as a steady flow process, a steady flow device. So by using the second assumption, we can use any simplified thermodynamic equation. Okay, now in the figure shows the cascade blade arrangement. We have two identical blade profile. Okay, so the region in enclosed by the green color line represent the control surface. So we divide into three surface: surface at the inlet of the cascade blade, surface within the cascade blade, and also control surface at the outlet of the cascade blade. So S represent the spacing distance. So we will have a pressure at the inlet of the cascade and also pressure at the outlet of the cascade, and the direction of both pressure are in different direction, because we will have pressure difference throughout the cascade blade. So P stand for pressure. So we also have the inlet flow velocity vector that represented by C1, outlet flow velocity vector represented by C2. And for the analysis of cascade forces, we will derive the equation for Y force and also X force. So now if you look at the direction of Y force and also direction of X force, so we will think about why the direction of Y force in horizontal direction. However, for the X force direction is in vertical direction. So now we will explain why the direction of Y force and so X force is as shown in the slide. Okay, so Y and X is referred as the applied force per unit depth. So so the figure shows a cross section of a rotor blade for a turbo machine. For this case, this example refer to the turbine. So we have 4 rows of the rotor blade, and the dash red color line represent the axis of the turbo machine, of the turbine. Okay, the green color arrow with parameter u, blade speed, represent the direction of the rotational movement, and also the value of blade speed. And also we have inlet flow velocity vector. Let's say we consider the last row rotor row of the turbine, and also we have C2, the outlet flow velocity vector. Now, due to the rotational movement of the rotor and also fluid flowing through the rotor, so we will have different kind of forces act to the turbine blades. First, we have X force in X direction, which is referred to the horizontal direction, and also we have Y force in Y direction or vertical direction, in vertical direction. So now, in order to to make sure that the physical properties of the parameter that involved in the cascade blade similar as in the figure that we discussed just now, so we just rotate the schematic diagram as shown by the second figure of the turbine rotor blade. So if you look in detail the parameter that involved in the figures, so we will have similar direction of flow, similar direction of forces, similar in the inlet of fluid at the inlet, the direction of fluid at the inlet and also direction of fluid at the outlet of the cascade blade similar. So that's why the direction of Y force and also the direction of X force in the schematic diagram for cascade blade, for Y force in horizontal direction, X force in vertical direction. So for every vector component, for C1 will consist of X component, Cx1, and also Y component, Cy1. So X represent component in X direction, Y represent component in Y direction. And also the angle for the vector C1 represented by alpha 1, flow angle at the inlet of the cascade blade. Similarly with the outlet velocity vector C2, also will have for a component X and also component Y, Cx2, Cy2. And the angle for the C2, which is represent the angle flow angle at the outlet, represented by alpha 2. Okay, so if we redraw again both triangle, so the triangle actually we call velocity diagram. So we can combine both diagram, the velocity diagram at the inlet and also velocity diagram at the outlet, in one velocity diagram. So C1, so we have X component, and also we have Y component, Cy1. For C2, so now we will have what I call two triangle with same what I call vector X component value. Okay, so now if you refer to the principle of continuity for axial flow, Cx1, the X component for vector C1 equal to Cx2, the X component for C2, equal to Cx, axial flow velocity. Okay, so if you refer to the trigonometry approach, we have this triangle. Let's say a triangle with an alpha angle in terms of vector C with X component Cx and Y component Cy. So we can use the basic trigonometry equation sin alpha equal to Cy divided by C, cos alpha equal to cx divided by c, tangent alpha equal to cy divided by cx. So from the continuity equation, so we get cx equal to c1 cos alpha 1 after we implement the trigonometry equation, cx2 equal to c2 cos alpha 2 equal to cx. So this is our first equation. That's why in the combined velocity diagram we have for both c1 and so c2 we will have same value in terms of component x. Cx equal to cx1 equal to cx2, which is the magnitude and also the direction of the x component is the same for both triangle for c1 also triangle for c2. So that's why we have this kind of combined velocity diagram. So now further, for c2 also we'll have y component cy2. So if we average both the velocity vector for c1 also c2, so we get another velocity vector, flow velocity vector that we call cm, mean flow velocity vector. So m represent mean velocity vector. So for this velocity vector for mean velocity, also we have the y component cym and also x component cxm equal to cx1 and equal to cx2, and the angle for the mean velocity vector represented by alpha m. Okay, now we just extract from the figures, from the cascade blade figures, we just extract individual inlet velocity diagram at point 1, which is referred to the inlet of the cascade blade. So this is the individual velocity diagram at the inlet of the cascade blade. So we have C1, so alpha 1, the component X for C1, component Y for C1. At the outlet, we have the velocity triangle or velocity diagram for C2. We have C2 alpha 2, the component for C2 CX2, component for CY C2, component Y for C2 CY2. And we can combine both diagram into one single velocity diagram for both inlet and also outlet of the cascade blade. Okay, now we try to start to derive the cascade force equation in terms of X force equation and also Y force equation. Okay, so force per unit depth applied in Y direction. So this is we want to start the derivation for Y force equation. Y equal to Fy divided by D. Fy stand for force in Y direction. D refer to depth. So later on we will explain what the meaning of the depth for the cascade blades. And Fy in terms of force formula equal to mass multiplied by acceleration of fluid in Y direction. And if we implement what we call the acceleration equation based on the momentum, so we'll get m dot the difference of velocity in Y direction divided by D. Further, by using the density equation, so we'll get rho v1 delta cy divided by D. And then by manipulating the equation for volume flow rate, so we get the last terms, the last definition for y equal to rho a cx delta cy divided by D. Okay, So you get this equation due to fluid's momentum. Okay, next, from the equation, so we get y equal to rho s cx cy1 minus cy2. Okay, so by using the trigonometry approach for C1 triangle and also C2 triangle, so you will get that y equal to rho s cx square tangent alpha 1 minus tangent alpha 2, which is the equation number 3. So equation number 3 is the general formula for y force. Okay, now we want to derive the equation for x. Force per unit depth applied in x direction equal to x equal to fx divided by d. Fx, force in x direction, divided by d, depth of the cascade blade. And by using the pressure equation, so you get fx equal to delta p times a, cross section area, divided by d. And also by changing the value of a, so we get delta p equal to s. S represent the spacing distance. So we get this formula due to the fluid friction different. Due to fluid pressure different. So A actually refer to the area of the cascade blade area where the fluid flow through the cascade blade, and the mass flow rate of the fluid perpendicular to the A area. So A actually equal to S times D. S represented by spacing distance and D represented by depth of the cascade blade. So now we will get the equation for X force, where X force equal to P2 minus P1 times S, spacing distance. So we get equation number 4. So later on I will explain about what is the meaning of the yellow area that represent for the section area or cross section area for the cascade blade. Okay, now I will explain what the meaning of the yellow cross section area of A that we already discussed previously when we explained about the equation of x. Okay, so x equal to fx divided by d equal to delta p times a divided by d equal to delta p s. So now A actually refer to the cross section area of the yellow square, where the formula for A actually S times D. S for spacing space, D for the depth of the cascade blade. Okay, so now the figure shows the actual physical properties of the turbine cascade blade. So this will be just for an example. So the m dot, the green arrow shows the direction of fluid flow throughout the cascade blade, and the direction of this mass flow rate of fluid actually is perpendicular to the cross section area of A. And the distance from the leading edge point, two identical leading edge point, is equal to the spacing distance S. Okay, S. And the height of the cascade blade actually equal to the depth of the cascade blade D. So now if we multiply S value with D value, so we'll get the area of the A, that we refer during our derivation of X equation. And the direction of flow through the cascade blade is perpendicular to this cross-section area. Okay, so now in terms of formula, A equal to ds, and if we rearrange the equation, so we get A divided by D equal to S. So substitute the equation into the X equation, so we'll get X equal to delta P times S spacing distance. So we get the final equation for X force, where delta P represent P2 minus P1 if you refer to the schematic diagram of the cascade blade. So X force equal to P2 minus P1 times spacing distance. Okay, next we will discuss about the energy losses, and one of the energy losses is the blade losses. So these blade losses also will contribute in the reduction of efficiency of a turbo machine. Okay, about blade losses. So blade losses in a turbo machinery actually will reduce the efficiency of the turbo machine. So now we need to consider blade losses, because we have to reduce this type of losses in order to obtain the optimum efficiency of a turbo machine. So there are 4 types of blade losses. First, we have surface or profile losses. Second, annulus losses. Third, secondary losses, and also leakage of fluid losses. So all these 4 types of blade losses is depend and I call affected by the blade profile condition. Okay, now about the blade surface or profile losses. So for blade surface losses, there are 2 factors that affect the blade surface losses value. First, we have the viscous force due to the moving fluid on the surface of the blade profile. And this factor will affect or will create the boundary layer, where the boundary layer actually is referred to the region that very close to the blade surface. Okay, let's see to the figures. So the figure shows a single blade profile, and the blue color arrow shows the fluid direction on the surface of the blade, and we will have different type of fluid flow on the surface of the blade as shown in the figures. So we can divide into 3 type of flow. First, at the beginning of the fluid flow on the surface of the blade, we have laminar flow, and then transition flow, and the final one is the turbulent flow. So we have 3 type of flow region. So you are for this type of flow regions, you already learn in fluid mechanics. Okay, so the boundary, the line that cover this 3 type of flow, we refer as the boundary layer, and the thickness of this boundary we refer as the boundary layer thickness. So this boundary layer thickness will affect the value of blade surface losses, because these properties affect the drag force, which is normally represented by D, drag force value, and also CD, drag force coefficient. The second parameter that affect by the value of boundary layer thickness is total pressure loss, delta P naught, which means if the boundary layer thickness increase, the drag force will increase, the total pressure loss also will increase, and this will decrease the overall efficiency of the cascade blade, and also the what we call the efficiency of a turbo machine. Okay, the second factor is about the pressure, static pressure of the fluid that flowing on the surface of the blade. So the pressure will increase with the flow direction of fluid. So this pressure normally refer to the static pressure of fluid flowing on the blade surface. So this phenomena will cause adverse pressure gradient according to the Bernoulli principle, where when the pressure increase, the fluid velocity will decrease, as according by the Bernoulli principle. So in order to understand this, I call this statement. So let me take three different section, which is refer S1, S2, S3. So we want to see what I call in terms of static pressure on different location of the fluid. Okay, so we have S1, S2, S3. If we plot static pressure throughout the condition, so we get the increased pressure profile throughout this flowing fluid on the blade surface. So the pressure increase. So throughout the increase of the pressure, so we will have the adverse pressure gradient, where this statement shows the slow development of pressure gradient as shown by the green triangle. So this effect of adverse pressure gradient will cause the slowdown of fluid flow in the boundary layer. Okay, so in this schematic diagram shows the velocity profile. Let us focus in the velocity profile diagram. Let us focus on the arrow with pink color, okay, as V1. And then when the pressure increase, we can see that in the velocity profile, the velocity will become V2, where in terms of the value, velocity will increase, V2 lower than V1. Further, when the pressure keep increasing at S3, so we will have reverse flow, where the velocity sometimes become zero, sometimes the velocity will have reverse direction, as represented by the arrow, pink color arrow, which is V3. Okay, so other than that, adverse pressure gradient also will promote separation, as shown in the figure. So separation means the streamline of fluid flow will not attach to the blade surface. So the streamline of the fluid will separate from the surface of the blade. So normally this separation region refer to the turbulent region, where there are a lot of vorticity, turbulence flow in the region, as shown in the figures. And this separation region also due to the reverse flow when the pressure of the fluid increase, as shown in the figure. Okay, so in order to describe profile losses, so we can use certain parameter. Normally we refer as drag coefficient, or we refer as profile losses. The symbol for drag coefficient is CD or CDP. CD or CDP equal to drag force divided by half density times mean velocity square times chord length distance. Okay, for second type of profile losses is the anomalous losses. Okay, so the figure shows the arrangement of blade on a rotor, and the second figure shows the what you call this front view of a rotor, where S refer as spacing and H refer to what I call the height of the blade. Okay, so normally annulus losses involve this boundary layer in specific region of the rotor, where normally refer to the boundary layer in the annular flow passage as shown in the figure. Okay, so annulus losses will involve the effect of the boundary layer in three different regions, which is number one, annular flow passage for outer and also inner surface as shown in the figures. The second one, cylindrical surface at the hub, and the number three is the losses involving cylindrical surface at the tip radii as shown in the figures. Okay, so the annulus losses described in terms of value can be described by using the drag coefficient, where the symbol for the drag coefficient for annulus losses is CdA. So CdA equal to 0.02 S over H, and S represent the blade spacing distance, H represent the blade height. So the value 0.02 in the equation normally obtained from the experimental investigation. Okay, the third type of the profile losses is the secondary losses. So the figure shows the arrangement of the two identical blades on a rotor. So normally secondary losses due to the vortex that develop in the fluid passage between the blades. So this vortex formed due to non-uniformity of velocity due to the blade profile, and cause the flow turning at the trailing edge as shown in the figures. Okay, so in order to describe the phenomena, let's look at the figures. So the region with the blue line refer what I call the velocity profile of the fluid throughout the blade passage. So we have what I call velocity profile in the x direction. Okay, so we can see that the red color line region shows the velocity profile when the flow turning at the trailing edge. So this phenomena will cause or will generate velocity component in y direction and also in z direction. Okay, so this phenomena we call vortex cavitation, where the mechanism will cause the secondary flow as shown in the figure. And this vortex cavitation or secondary flow will cause the block of flow rate of the fluid, and also will cause damage to the rotor blade due to the vibration and so on. And this will cause further dissipation of energy in blade passage, which cause pressure losses increase, pressure rise decrease, and then will reduce the efficiency of the turbo machine. So in order to describe the secondary losses, we can use this formula, where the secondary losses can be described by using drag coefficient for secondary losses with symbol CDS. In terms of formula, CDS equal to 0.018 CL lift coefficient square. So CL stand for lift coefficient. Okay, the last type of blade profile losses is the leakage of fluid losses. So the figure shows the cross-section drawing of the compressor, where the figure shows the stator vane or stator blade, where the stator blade attached to the casing and doesn't move. And the second is the rotor blade, where the rotor blade will move based on the rotational movement of the rotor. Okay, if you look by using different view, front view of the rotor, in the second figure, you can see that the figure shows the casing of the compressor and also the rotor of the compressor, including the blades. So we have in the figures, the second figure, various type of flow. We have radial flow and also leakage flow. So our concentration or our focus on the second figure is to the leakage flow, where the flow refer to what I call leakage flow refer to the flow that occur in the area or in the region between the blade tips and also the inner surface of the casing. So the leakage of fluid losses is referred to to the losses that caused by the leakage flow. Okay, so if we look at different view, plan view of the rotor, we can see that we have tips leakage flow in the figure. So the flow throughout this area on the top of the what I call rotor or blade tips. Okay, so leakage flow losses actually refer to the leakage of fluid around the tip through the narrow passage formed between the blade tip and also the casing, as I mentioned before. So if you look to the schematic diagram of two identical cascade blade, so the what I call the red color arrow represent the flow at this region. So to describe the leakage flow losses, so we can use the direct coefficient for the leakage flow, where direct coefficient for the leakage flow losses CDL equal to 0.29 TC divided by H times CL leaf coefficient power of 3/2, where TC refer to the tip clearance, the distance between the inner surface of the casing and also the tip of the blade. So H refer to the blade height. Okay, so that's okay. To test your understanding about the part 3 for chapter number 2 about the cascade blade, please answer the question below. First, what is the major factor for the X-force equation? Number 2, what is the major factor for the Y-force equation? And number 3, the cause of turning flow at the trailing edge in the secondary losses. So please answer the question. You have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. The clue also is given in the link. That's all for part number 3. Assalamualaikum warahmatullahi wabarakatuh.